All right, welcome to The Explainer. Today, we're going on the ultimate cosmic tour of our home address in the universe, the city of stars we all live in, the Milky Way galaxy. So let's just jump right in.
You know, if you've ever gotten away from the city lights out in the country on a really clear night, you've seen it. That hazy, glowing river of light stretching across the whole sky. For thousands of years, people have looked up at that exact same view. But what you're seeing isn't just a pretty cloud. You're looking at the edge of our own galaxy from the inside out.
So it's this thing we see all the time, this beautiful streak of light. But what are we actually looking at? What is the true nature of this gigantic structure that we call home?
To start, let's just get our bearings. We're going to look at where the name came from and, more importantly, find our exact address in this massive city of stars.
So where does a name like Milky Way even come from? Well, it actually goes back to an ancient Greek myth, a story about the goddess Hera spilling her milk across the sky and creating this, well, milky path. But they weren't the only ones. In China, it's called the Silver River. In Sanskrit, it's the Ganges of the heavens. It's this beautiful idea that no matter the culture, everyone looked up and saw a kind of celestial river flowing through the night.
Okay, so where is our house on this cosmic river? Well, we definitely don't live in the bustling downtown area. Not even close. You could say we live out in the galactic suburbs, about 27,000 light-years from the crazy busy center. We're kind of tucked away on a smaller, local lane, a minor spiral arm called the Orion Spur.
And get this, we are not sitting still. Just like the Earth is zipping around the Sun, our entire solar system is careening around the center of the Milky Way at a speed that's just hard to wrap your head around. We're talking 514,000 miles per hour.
But here's the crazy part. Even at that insane speed, the galaxy is so unbelievably huge that it takes us about 230 million years to make one single trip around. That's a galactic year. To put that into perspective for you, the last time our solar system was in this exact spot, the very first dinosaurs were just starting to show up on Earth. So we've got our cosmic address. Now, what does the whole building actually look like? Let's get into the anatomy of our spiral home.
So you've probably heard that the Milky Way is a spiral galaxy, but it's a specific kind, a barred spiral galaxy. For the longest time, astronomers just assumed the center was a big ball of stars. But it's actually a dense, bar-shaped structure, and the arms spiral out from the ends of that bar. And funny enough, we only really confirmed this in the 1990s.
And the scale, it is just staggering. The main visible part of the galaxy, the disk with most of the stars we can see, stretches about 100,000 light-years from one end to the other. Now this is one of my favorite ways to picture the scale of it all. It makes it so much more real. If our galaxy was the size of a frisbee, its thickness would be about the same as a single sheet of paper. Think about that. We're living inside a giant cosmic pancake.
But it's not a perfectly flat pancake. Thanks to some amazing data, we now know the disk is actually warped and twisted. It wobbles, kind of like a spinning top that somebody bumped into. And the reason why? The best guess is that our galaxy had a run-in with a smaller one a long time ago. Its gravity essentially gave our disk a little nudge, and it's been wobbling ever since.
So we've got this giant, wobbly, spinning disk of stars. But this is where the story takes a turn into the completely mysterious. Because what you see is nowhere near the whole story. Okay, just look at this chart. If you could somehow weigh the entire Milky Way, this is what you'd find. All the stars, all the planets, all the gas and dust, everything we can see with our best telescopes, that makes up a measly 10% of the galaxy's mass. So, what in the world is the other 90%?
Well, it's a mysterious substance we call dark matter. We have no idea what it is, we can't see it, we can't touch it, we can't detect it, but we know it's there. Why? Because without its massive gravitational pull, our galaxy would have flown apart billions of years ago. The stars on the outer edges are moving so fast they should have been flung off into space. Dark matter is the invisible cosmic glue holding the entire thing together. It's truly the great, humbling secret of our galaxy.
Okay, so from the giant invisible mystery that surrounds us, let's travel all the way to the heart of the galaxy, to a point of extreme violence and gravity that everything we see is orbiting around. Right at the galactic center, hidden behind these thick clouds of dust and gas, there lurks a monster. It's a supermassive black hole, and its name is Sagittarius A star. Now, of course, we can't see it directly, but we can see the stars near it whipping around an invisible point at unbelievable speeds. That's how we know it's there.
And how massive is it? This single object has the mass of 4 million of our suns. All of it crushed down into one single point of infinite density.
But here's the part that really just breaks your brain. All of that mass, 4 million suns worth, is packed into a space that's only about 20 times wider than our own sun. The density is it's unimaginable. This thing is the gravitational anchor for our entire galaxy.
You know, our galaxy isn't some static island just floating in space. It has a pretty violent past, and it's hurtling towards an even more dramatic future.
So let's look at the life story. It all starts way back, about 13.6 billion years ago, not too long after the Big Bang. And our galaxy didn't just appear. No, it grew through what we call galactic cannibalism, basically eating smaller galaxies that got too close. But its biggest meal is yet to come. Right now we are on a direct collision course with our big neighbor, the Andromeda Galaxy, and in about 4 billion years, they're going to start merging. It'll be a slow-motion cosmic dance of destruction and creation, and when it's all over, they'll form one giant new galaxy. Some astronomers have already nicknamed it Milkometa.
So let's just recap the sheer scale of it all one more time, because these numbers are just wild. Up to 400 billion stars, at least that many planets. A single trip around the galaxy for us takes 230 million years, and we've only been around the block about 20 times. And we're doing it all while moving it over 1 million miles per hour. It's just mind-bending.
And all of this, it brings us to the final, and maybe the most profound question there is. We live in this galaxy with hundreds of billions of suns, orbited by at least that many worlds. And as we look out from our tiny little home in our quiet little neighborhood, you just have to wonder, in all of this vastness, are we the only ones looking back?
Have you ever found yourself far from the city lights, maybe camping out under a truly pristine, clear sky and just gazed up into the heavens?
Oh, absolutely. It's one of those experiences, isn't it?
It really is. And what you see stretching across the cosmos like this soft, glowing, seemingly endless band of light, it's just breathtaking.
Truly. It's a sight that connects us, I think. Human across time, across cultures.
Yeah. And that faint, luminous streak, it isn't just some beautiful part of the night sky. It's our cosmic address.
Exactly. It's our home. The Milky Way galaxy itself, the very galaxy our solar system is a part of, visible to the naked eye. It's inspired awe, curiosity, and countless stories for, well, forever.
And that's exactly our mission today here on The Deep Dive. We're taking you on a bit of a shortcut, to getting really well informed about our own galactic home.
We're going to unpack some of the most fascinating, maybe surprising, and truly mind-blowing facts about the Milky Way.
Guiding you from its ancient, almost mythical origins, all the way to its dramatic, distant future.
Our goal is to help you connect the dots. Between the Milky Way's immense scale, its mysterious unseen components, and the incredibly dynamic processes always at play.
So you'll understand not just what makes our galaxy special, but maybe why it matters to us right here on this tiny planet.
So prepare for some aha moments, hopefully. We'll journey through its history, explore some of its, bizarre contents, and chart its incredible journey through the universe.
And don't worry, we promise to deliver all this without it feeling like you're drowning in information overload. You'll be talking about this stuff tomorrow. Let's dive in.
Okay, where to begin?
Let's start with the absolute basics, getting acquainted with our home galaxy. And what better place than its name, Milky Way. It's much more evocative than, say, Galaxy 001, right?
Absolutely. And the name Milky Way, it has really ancient roots. It stems all the way back to ancient Greek mythology.
Oh, yeah. The Greek myths are always wild. What's the story here?
Where the most popular legend tells of the goddess Hera, queen of the gods.
Yeah.
Right? She was reluctantly nursing the infant Heracles.
Heracles. Okay. Strong baby.
Exactly. The story goes, the powerful little demigod sucked a bit too strongly, maybe, and Hera pushed him away. In doing so, some of her divine milk spilled across the night sky.
Ah, okay. Cosmic spillage.
Precisely. And just like you could see it with your own eyes today, that spillage created this luminous, milky white band across the heavens. And the name, it just stuck. Makes sense when you look up, doesn't it?
It really does. And it wasn't just the Greeks who saw it that way, was it? I mean, that milky appearance must have struck a chord elsewhere, too.
That's one of the really fascinating parts. It shows this kind of universal human response.
Yeah.
Across totally different civilizations, you see remarkably similar descriptive names, even without any contact between them.
Like what? Give us some examples.
Okay, so in the Kalahari Desert in southern Africa, it's called the backbone of night. Isn't that beautiful?
Wow, yeah. Backbone of night.
In ancient China, it's the Silver River. Sanskrit traditions in India call it Ganges of the heavens, linking it to their sacred river.
Connecting the earthly and the celestial.
Exactly. The Romans, ever practical, called it the Via Lactea, the Milky Road, like a path through the stars.
A road, okay.
And the ancient Greeks, who gave us the name we use, called it the Milky Circle. And actually the word galaxy itself, it comes directly from the Greek word for milk, galactos.
No way. So galaxy literally means milky.
Pretty much. It's this amazing connection across time and language, all stemming from just looking up and describing what they saw.
So for thousands of years, people looked up, saw this band, maybe told these stories, but what did they think it actually was? It wasn't always understood as stars, right?
No, not at all. For millennia, its true nature was a mystery. Many cultures saw it as a path for spirits, maybe a river, a divine serpent, all sorts of things.
Makes sense. It does look kind of ethereal.
But the ancient Greek philosopher Democritus, around 400 BC, he was the first known person to suggest something radical. He proposed it was actually made up of countless individual stars.
Just based on thinking about it, no telescopes back then.
Nope. Purely a philosophical deduction. A brilliant leap of imagination, really. But it wasn't until Galilei in 1610 that we got confirmation.
Right, with his telescope.
Exactly. He turned his new, kind of rudimentary telescope towards the Milky Way, and bam! He resolved that faint band of light into countless, distinct, individual stars. A truly revolutionary moment. Physical proof.
And even then, understanding it was stars was just the beginning, right? Because for a long, long time, people thought our galaxy was everything, the whole universe.
Yes. It's really mind-boggling to think about now. For centuries after Galileo, even as telescopes got better, the prevailing view was that the Milky Way was the entire universe, just this one vast island of stars in an empty void.
So when did that change? When did we realize there was more out there?
That fundamental shift happened only about 100 years ago, in 1923, thanks to the work of Edwin Hubble.
Hubble, okay. The telescope guy. Well, the guy the telescope is named after.
Right. He made a groundbreaking discovery using special types of stars called Cepheid variables in what was then called the Andromeda Nebula.
What's special about those stars?
They pulsate, they get brighter and dimmer, and crucially, the speed of their pulsation is directly linked to their true brightness, their absolute luminosity. This allowed Hubble to calculate their distance accurately.
Ah, a standard candle, sort of?
Exactly. And he proved unequivocally that the Andromeda Nebula wasn't a gas cloud inside our Milky Way. It was a vast, independent galaxy millions of light years away.
Wow. So overnight, the universe just exploded in size.
Pretty much. It fundamentally expanded our cosmos, proving there were hundreds, eventually billions, of other galaxies beyond our own. A total paradigm shift.
It's just fascinating how our ancestors saw the same sky, imagined myths, and then science, in just the last century, really, completely rewrote the story. Incredible.
It really puts into perspective how much we've learned and how recently.
All right, now let's try, and I mean try, to wrap our minds around the sheer size and scale of this thing. Because saying the Milky Way is big feels like, well, the understatement of the millennium.
It truly is. It's colossal, this disk structure. And grasping its sheer immensity from our vantage point inside it is incredibly difficult.
So give us the numbers. How big are we talking?
Okay, so NASA usually states the main disk is about 100,000 light years across. A light year being the distance light travels in a year, which is already huge, about 6 trillion miles.
100,000 light years. Okay, that's big.
But wait, it gets bigger. Newer observations, especially from missions like the Gaia satellite, which is mapping stars with incredible precision, suggest the faint outer region scattered stars, gas clouds, extend much further out.
Further than 100,000.
Yeah. Some estimates push the total diameter to maybe 150,000 or even up to 200,000 light years across when you include those wispy outer tendrils.
200,000 light years, doubling the size. That's insane. Okay, so it's incredibly wide. How thick is it? Is it like a big sphere? Or?
Not at all. It's often described as a cosmic pancake. It's a pretty good analogy, actually. The main disk is relatively flat, only about 1,000 light years thick, maybe a bit more in some places.
Only 1,000. That sounds like a lot, but compared to 200,000 wide, that's really flat.
Extremely flat, but it's not uniform. It bulges significantly in the center. There's this thick central core, the galactic bulge, where it's maybe 10,000 light years thick, densely packed with stars.
Okay, so huge to us, but you mentioned Andromeda, Hubble. How do we stack up against other galaxies out there? Are we a giant, average, or what?
We're respectable.
Yeah.
Definitely massive by our standards, but on the cosmic scale, the Milky Way is generally considered a medium-sized spiral galaxy.
Medium size, seriously?
Yep. Our neighbor Andromeda, the one Hubble studied, is actually a bit larger, maybe 220,000 light years across.
Okay, so our neighbor is bigger.
And then you get the true behemoths.
Yeah.
The galaxy IC 1101, for instance, is maybe 6 million light years across and has over 100 trillion stars.
6 million, 100 trillion stars. Okay, my brain just broke.
And others, like the elliptical galaxy M87, that's nearly 1 million light years across. Hercules A is about 1.5 million light years wide. So yeah, we're definitely not the biggest fish in the cosmic pond, more like a good-sized tuna in an ocean of blue whales.
We need analogies. My brain can't hold these numbers. Help me visualize this. Shrink it down.
Okay, let's try this. Imagine our entire solar system, sun, planets, everything out to the Oort cloud, is shrunk down to the size of a US quarter.
Okay, quarter-sized solar system. Got it.
On that scale, the sun itself will be a microscopic, invisible speck of dust.
Wow.
But the Milky Way galaxy, on that same scale, it would span the entire continental United States, from Los Angeles to New York.
Whoa. Okay, that helps. Kind of terrifyingly, but it helps.
Or another one. If the Milky Way had the diameter of a frisbee, its disk thickness would be comparable to a single sheet of paper. That shows how incredibly thin it is relative to its width.
A paper-thin frisbee the size of the US. Okay. And here's something that always gets me. We can't actually take a picture of it, can we? Not a full top-down spiral shot like you see everywhere.
That's a crucial point, and yeah, it surprises a lot of people. Since we are inside the Milky Way, about 26,000 to 28,000 light years from the center, we just can't get an outside perspective.
It's like trying to take a selfie of your entire house while standing in the living room.
Exactly. You only get partial views. Any stunning image you've ever seen of a complete spiral galaxy labeled Milky Way is either a picture of a different, similar-looking spiral galaxy like Andromeda, or, more commonly, it's an artist's incredibly detailed interpretation based on all the data we've gathered from inside.
An artist's impression. Based on science, but still, not a photo.
Right. To get far enough away to take a real full picture, a spaceship traveling at the speed of light would need tens of thousands of years just to get to a good vantage point. It's just not feasible.
That's incredible, the sheer immensity. It makes you feel tiny, but also kind of special that we can even figure this stuff out from our little corner. It's humbling.
It really is. And this scale leads right into its shape. It's not just a simple flat disk. As we sort of hinted, the Milky Way is officially classified as a barred spiral galaxy.
Barred spiral. Okay, break that down. What's the barred part?
So, unlike a regular spiral galaxy that might have arms curling directly out from a round central bulge, ours has a distinct, elongated, bar-shaped region of densely packed stars running right through its core.
A bar of stars, like a big rectangle in the middle.
Sort of, yeah. If we could look down on it from above, this bar would be a really prominent, bright feature, maybe 27,000 light years long. It's not subtle, it's a major structural component. It significantly affects how gas and stars move near the center. This was only really confirmed in the 1990s using infrared telescopes that could peer through the dust hiding the core.
Infrared, right, cutting through the dust. Okay, so there's a bar. Where do the spiral arms come from then?
They extend outwards from the ends of that central bar. Several major spiral arms curve gracefully around as the galaxy rotates.
And these arms aren't just static patterns, right? They're active regions.
Exactly. Think of them as density waves or cosmic traffic jams. Gas and dust pile up in these regions, compressing, and that triggers massive bursts of star formation. So the arms are where most of the young, bright, hot stars are born.
Star nurseries.
Precisely. Now, identifying the exact number and shape of the arms from inside is tricky, but generally we talk about 4 main arms: Sagittarius Carina, Perseus, Scutum Centaurus, and Norma Cygnus.
And where are we in all this? Are we on a main arm?
Nope. Our solar system is actually located on what's called the Orion Arm, or sometimes the Orion Spur. It's considered a smaller, minor branch, or spur, nestled between the larger Sagittarius and Perseus arms.
So we live in the galactic suburbs, on a side street.
Kinda, yeah. Not on the main galactic highway. The stars in the arms tend to be the bigger, brighter ones that burn out faster, which helps illuminate the arms and make them stand out.
Okay, so disk, bar, arms. What else? I remember reading about a halo.
Yes, absolutely. Surrounding the entire main disk, extending far above and below it, is a faint, roughly spherical halo.
What's in the halo?
It's much less dense than the disk. It contains very old stars, often moving in highly elliptical orbits, plus scattered gas and dust. And importantly, it's home to globular clusters.
Globular clusters. Those are the really old, dense balls of stars. Yeah.
Exactly. Ancient collections of hundreds of thousands, sometimes millions of stars packed tightly together. Some are over 10 billion years old, true relics from the Milky Way's early formation. They act like cosmic fossils, telling us about the galaxy's youth.
And adding one more layer of complexity. You mentioned the cosmic pancake isn't perfectly flat, it's warped.
That's right. This is a really cool, relatively recent discovery that shows how dynamic our galaxy is. The Milky Way's disk isn't perfectly flat. It's significantly warped, especially towards the outer edges. And it actually wobbles as it spins, kind of like a spinning top that's slightly off kilter.
Our whole galaxy is wobbling. What causes that? Did we bump into something?
That's the leading theory. While it's not definitively proven, researchers strongly suspect this warp and wobble are caused by gravitational interactions, maybe even past glancing collisions with other galaxies.
Like which ones?
The main suspects are the Large and Small Magellanic Clouds. These are our biggest satellite galaxies currently orbiting the Milky Way. Their gravity is constantly pulling and tugging on our galaxy's outer disk in a sort of cosmic tug-of-war, subtly distorting it and causing these ripples or warps.
So our neighbors are literally bending us out of shape.
Basically, yeah. The Gaia mission mapping star positions and movements with incredible accuracy has been crucial in confirming this warped structure. It sees the stars moving in ways that perfectly match these warped models.
Wow. A warped, wobbling, barred spiral pancake. Okay, so now that we have a picture of the structure, let's dive into what actually fills this incredible place. What's it made of?
Right. Let's unpack the components.
First up, the stars. We know there are billions. But what's the actual estimate? How many suns are we sharing this galaxy with?
It's a truly staggering number. Our galaxy is a bustling metropolis of stars. Current estimates range somewhere between 100 billion and 400 billion individual stars.
100 to 400 billion, that's a huge range. Why is it so hard to pin down?
It's incredibly difficult, mainly because we're trying to count them from the inside, remember? It's like trying to count every single person in a massive crowded city while standing in the middle of Times Square.
Okay, yeah, bad view.
Exactly. Thick clouds of interstellar dust and gas, especially concentrated in the spiral arms and towards the galactic center, block our view in visible light. Light just can't penetrate very far through that stuff, maybe only 4,000 to 6,000 light years, effectively.
So how do astronomers see past the dust?
They use other wavelengths of light that can cut through the dust, primarily radio waves and infrared light. Using huge radio telescopes and infrared space observatories, we can peer much deeper into the galaxy and map structures we'd otherwise miss.
But even with that, it's still an estimate.
Still an estimate, yeah. The galaxy is just too vast and complex to do a perfect star-by-star census. For context, the Gaia satellite, which has produced the most detailed map yet, has cataloged the positions and motions of about 1.8 billion stars.
1.8 billion? That sounds like a lot.
It is, but scientists believe that's still only about 1% of the total number of stars in the Milky Way.
1%? Wow. Okay, so out of those hundreds of billions, how many can I actually see on a good night? Just with my eyes.
From any single spot on Earth, assuming perfect conditions, really dark sky, no moon, no light pollution, you could typically see only about 2,500 individual stars with the naked eye.
2,500? That feels like so few compared to 400 billion.
It's an incredibly tiny fraction, something like 0.000000025%. So when you look up at the stars, you're really only seeing the very brightest, closest neighbors, the tip of a vast cosmic iceberg.
And it's not just a static collection, right? You mentioned star formation. The Milky Way is actively making new stars.
Absolutely. It's a dynamic, ongoing star factory. New stars are continuously forming, especially in those dense regions of gas and dust we call nebulae, giant molecular clouds.
Stellar nurseries.
Exactly. Astronomers estimate that, on average, about 7 new stars ignite in our galaxy every single year. It's a steady process of cosmic creation.
And these stars live and die, right? That's part of the cycle.
Yes. Stars evolve through different stages. The really massive ones end their lives in spectacular explosions called supernovae. These are incredibly important events.
Why are supernovae so important, besides being dramatic?
They do 2 crucial things. They release immense energy, but more importantly, they forge and then scatter heavy elements out into the galaxy elements heavier than hydrogen and helium, which are essential for making planets like Earth and ultimately us.
So stars create the ingredients for future stars and planets when they die.
Precisely. It's a continuous cycle of cosmic recycling. Birth, life, death, and rebirth from the ashes.
And are all stars like our sun? Or is there a lot of variety?
Oh, incredible variety. Besides single stars like our sun, there are binary systems, 2 stars orbiting each other, which are actually very common, but also triple, quadruple, even more complex systems.
Stars orbiting stars, orbiting stars.
Sometimes, yeah.
Yeah.
And stars themselves come in all sorts of types, classified by their spectral type letters like O, B, A, F, G, K, M. This basically tells us their temperature, color, size, and mass.
Like O stars are hot and blue, M stars are cool and red.
Exactly. The O and B stars are massive, hot blue giants burning incredibly bright, but living relatively short lives. Our sun is a G-type star, kind of average. N-type stars are small, cool red dwarfs that can live for trillions of years. Astronomers use tools like the Hertzsprung-Russell diagram to plot these different types and understand their life cycles.
And I think I read about different populations of stars, like older and younger ones.
Yes, broadly speaking, we talk about two main stellar populations. Populationized stars are younger, generally found in the disk, richer in heavy elements, what astronomers call metals, and orbit in relatively circular paths.
Like our sun.
Like our sun, yes. Population 2 stars are much older, found mostly in the halo and the central bulge, are metal poor, meaning they formed early before many supernovae enriched the galaxy, and often have more elliptical tilted orbits. Studying these populations helps us piece together how the galaxy formed and evolved over billions of years.
It really drives home the point. With hundreds of billions of stars and new ones forming all the time, the sheer probability of planets, maybe even life, seems, well, huge.
It certainly fuels the imagination, doesn't it?
Okay, now for the really weird part. You said stars, gas, dust, that's what we see. But apparently that's only a tiny fraction of what's actually there.
This is where it gets truly mind-bending.
Yes.
Everything we can see or detect directly, all the stars, gas, dust, planets, everything made of normal atoms makes up only about 5% to maybe 10% of the Milky Way's total mass.
5 to 10%. So what's the other 95%?
That's the trillion-dollar question. The vast majority, an astonishing 85% to 90%, is believed to be made of a mysterious, invisible substance we call dark matter.
Dark matter. Okay, I've heard the term, but invisible. How do we even know it exists if we can't see it? This sounds like science fiction.
It does feel like it sometimes, but the evidence is gravitational. Dark matter doesn't interact with light. It doesn't emit, absorb, or reflect it, so telescopes can't see it directly. We only know it's there because of its powerful gravitational pull on the things we can see.
Okay, so how does that work? How do we see its gravity?
For decades, astronomers noticed something strange about how galaxies rotate. Stars in the outer regions of galaxies, including our Milky Way, are orbiting much, much faster than they should be based on the gravity of just the visible stars and gas.
Faster, so they should just fly off into space.
Exactly. According to Newton's laws and the amount of visible mass we can measure, those outer stars should have escaped the galaxy's pull long ago. But they haven't. They're still orbiting.
So there must be extra gravity holding them in.
Precisely. There has to be an enormous amount of unseen mass providing extra gravitational pull, keeping the galaxy bound together. That unseen mass is dark matter. It's like seeing leaves swirling in a pattern and knowing the invisible wind is causing it. We see the effect, not the cause itself.
So it's like this invisible scaffolding holding the entire galaxy together.
That's a great way to put it. And it doesn't seem to clump together like normal matter does to form stars or planets. Instead, it forms a vast, roughly spherical, invisible halo that surrounds the entire visible galaxy, stretching far beyond the edges of the stellar disk.
An invisible halo making up most of the galaxy's mass.
Yep. This dark matter halo is absolutely critical. Without it, galaxies like ours would literally tear themselves apart as they rotate.
And the numbers again? How much mass are we talking?
The total mass of the Milky Way is estimated to be around 1.3 trillion times the mass of our sun. Of that, maybe 1.1 to 1.2 trillion solar masses is dark matter. Only around 100-200 billion solar masses is the normal baryonic matter that makes up stars, gas, dust, and us.
So it outweighs the normal stuff by like 5 or 10 to 1.
At least, it's the dominant component by mass. Yet we have almost no idea what it actually is. It's not just dim stars or gas clouds we haven't found. It has to be something fundamentally different, some kind of particle that barely interacts with normal matter except through gravity.
Still one of the biggest mysteries in science, then.
Absolutely, one of the very biggest. Scientists are throwing everything they have at trying to detect dark matter particles directly in underground labs, or create them in particle colliders, or find other indirect evidence. But so far, no definitive detection. What's fascinating is that our entire cosmic structure, the existence of galaxies themselves, seems to depend on this invisible, enigmatic stuff.
It really challenges your perception of reality, doesn't it? Knowing that most of the universe, most of our own galaxy, is made of something we can't see or understand.
Wow, okay. Moving on from the invisible, what about the visible stuff besides stars, gas and dust. Right. Beyond the stars and the dark matter, the Milky Way is also incredibly rich in gas and dust. This interstellar medium makes up about 10–15% of the visible matter.
So a significant chunk of the stuff we can see.
Definitely. And it's overwhelmingly hydrogen and helium, the lightest elements, mostly left over from the Big Bang. But there are heavier elements mixed in too.
And this gas and dust isn't just floating around, it's important.
Vitally important. It's the raw material from which new stars and planets form. It also affects how light travels through the galaxy, absorbing and scattering starlight, which is why distant things look dimmer and redder, and why parts of the Milky Way look dusty or obscured.
You can actually see that dustiness on a dark night, right? That band isn't perfectly smooth.
Exactly. That hazy, uneven look of the Milky Way band in the sky is partly due to those vast clouds of interstellar dust blocking the light from stars behind them.
And I heard something really weird about this interstellar medium. Something about toxic grease. What is that?
Yeah, it sounds bizarre, doesn't it?
Yeah.
But it's a real thing, surprisingly. Astronomers discovered that swirling through interstellar space is a significant amount of complex, oily organic molecules, specifically aliphatic carbon compounds. Think long chains of carbon atoms.
How's space oil?
Kind of. This dirty grease is produced in the atmospheres of certain types of dying stars and then blown out into space. A recent study found these compounds could account for maybe 1/4 to 1/2 of all the carbon floating around in interstellar space, way more than previously thought.
Wow. And carbon is key for life.
Exactly. While toxic grease sounds unappealing, finding such an abundance of complex carbon molecules just floating around freely is actually really exciting for the prospects of life elsewhere. It means the basic building blocks are common. Maybe the ingredients for life are widespread.
So less toxic, more potential.
Potentially. It certainly makes the galaxy seem like a more fertile place.
Are there other specific features made of this gas and dust, like nebulae?
Yes, absolutely. Besides the star-forming nebulae, you have things like dark nebulae. These are clouds so dense with dust that they completely block the light from stars behind them. They appear as eerie, dark patches or silhouettes against the bright backdrop of the Milky Way. The Coalsack Nebula in the southern sky is a famous example.
Like holes punched in the sky.
Exactly. But they're not empty. They're full of cold gas and dust, potential future star factories.
And this leads us to the elements themselves. Hydrogen, helium, carbon, the metals.
Right. Remember, in astronomy, metals means anything heavier than hydrogen and helium. Carbon, oxygen, nitrogen, silicon, iron, all the stuff needed for rocky planets and life are considered metals.
And these come from stars.
They're forged inside stars through nuclear fusion during their lives, and especially during their explosive deaths, like supernovae. These events blast the newly created heavy elements out into the interstellar medium.
The recycling program again.
Exactly. Each generation of stars enriches the gas with more metals. So the metallicity, the abundance of these heavy elements generally increases over time and varies across the galaxy. It's a key tracer of galactic history and evolution. Regions with lots of star formation are more metal-rich.
So the Milky Way is constantly churning, recycling material, building complexity.
That's the picture. It's a dynamic, evolving ecosystem on a cosmic scale. This continuous recycling ensures the ongoing formation of new stars, new planets, and keeps the potential for life simmering throughout the galaxy. These components, gas, dust, elements, grease, are the fundamental ingredients.
Okay, so our galaxy is this dynamic, evolving place, and we're moving within it, right? Our solar system isn't just sitting still. We're on this grand tour.
We absolutely are. Think of it like being on a giant cosmic carousel that's been spinning for billions of years.
Where exactly are we on this carousel?
Our solar system, the sun and planets, were located about 26,000 to 28,000 light years away from the galactic center, the very heart of the Milky Way.
So roughly halfway out from the center to the visible edge.
A bit more than halfway, yeah. And as we mentioned, we're nestled on the inner edge of a minor spiral arm, the Orion arm, or Orion spur. We're not on one of the galaxy's main thoroughfares.
The galactic side street. And how fast is this carousel spinning? How fast are we moving?
Hold on to your hat. We are hurtling through space at an average speed of about 220 to 230 kilometers per second.
Per second. Okay, translate that. Miles per hour.
That's roughly 500,000 to 514,000 miles per hour relative to the galactic center.
500,000 miles an hour? That's insane. How are we not all flying off our chairs?
Well, everything, the sun, Earth, us, is moving together so we don't feel the speed directly, just like you don't feel the speed of a plane cruising at 500 miles per hour. But to put it in perspective, an object moving that fast could zip around Earth's equator in under 3 minutes.
Okay, that's fast. But the galaxy is huge. So even at that speed, one lap must take forever.
Forever is about right, on human timescales. Despite that incredible speed, the sheer scale of the orbit means it takes our solar system approximately 230 to 240 million years to complete just one full orbit around the galactic center.
230 million years. That's,
Yeah.
wow. That's called a galactic year, right?
Exactly. One galactic year, just one trip around.
So our solar system is about 4.6 billion years old. How many laps have we made? How many galactic birthdays has the sun had?
Only about 20, give or take.
Yeah.
In its entire 4.6 billion year lifetime, the sun has completed only about 20 orbits around the Milky Way.
Only 20 times around. It feels like we should have done more.
It puts cosmic time in perspective, doesn't it? For another reference point, the dinosaurs went extinct about 65 million years ago. Since then, our sun has traveled only about 1/3 of the way around its current orbit.
We're still relatively new travelers on this path then.
In cosmic terms, absolutely.
And is our path perfectly flat within that galactic pancake? Or do we move up and down too?
We bob up and down. The solar system's orbit isn't perfectly confined to the galactic plane. As we circle the center, we gently weave above and below the plane in a slow, wave-like motion.
Like riding a ripple.
Kind of, yeah. It'd take maybe 60 million years or so to go from the peak above the plane, down through it to the lowest point below, and back up. It's thought to be caused by the gravitational pull of the spiral arms, or maybe clumps of dark matter. But we stay well within the main disk.
Okay, and this relates to why the Milky Way looks like a tilted band in our sky, doesn't it? Our solar system isn't aligned with the galaxy's plane.
Precisely. The plane of our solar system, the ecliptic, where the planets orbit the sun, is tilted at a significant angle about 60 degrees relative to the main plane of the Milky Way galaxy.
Ah, so we're looking across the disk at an angle.
Exactly. That's why the Milky Way stretches across our night sky as a bright angled band rather than a straight line overhead or along the horizon. It's all about our tilted perspective from within this moving, wobbling cosmic carousel.
Okay, so we're orbiting the center. Let's talk about that center, the galactic core. There's something really big and powerful lurking there, isn't there?
Indeed. At the very heart of our Milky Way lies a supermassive black hole. Its name is Sagittarius A, pronounced Sagittarius A star.
Sagittarius A. And when we look towards the constellation Sagittarius, towards the brightest, widest part of the Milky Way band, we're looking right at it.
You're looking in its direction, yes. But you can't actually see Sagittarius A itself, at least not in visible light.
Why not? Is it too small? Too far?
It's hidden. It's obscured by incredibly thick clouds of interstellar dust and gas, plus countless intervening stars that block the visible light from reaching us. It's like trying to see a candle through thick fog.
So how do we find it if we can't see it?
It was first detected indirectly back in 1974 through strong radio waves it was emitting. Unlike visible light, these radio waves can penetrate the dust clouds.
Ah, the radio waves gave it away.
Exactly. They acted as a kind of smoking gun, suggesting there was something incredibly energetic and compact at the precise center of the galaxy, likely surrounded by a swirling disk of hot gas emitting those radio waves.
But detecting radio waves isn't the same as proving it's a black hole. How is that confirmed? I know this was a huge discovery, right?
Yeah.
Nobel Prize worthy.
Absolutely. Confirming it was indeed a supermassive black hole took decades of painstaking observation and earned the 2020 Nobel Prize in Physics for Andrea Ghez and Reinhard Genzel.
What did they do?
They use powerful infrared telescopes again. Infrared light can pierce the dust better than visible light to track the movements of individual stars orbiting very close to that central radio source, Sagittarius A.
They watched stars orbiting something invisible.
Precisely. And what they saw was astonishing. Some of these stars were whipping around this unseen object at incredible speeds, thousands of kilometers per second. Some were clocked at over 7,650 kilometers, which is about 2.5% the speed of light.
Wow, nothing but a black hole can make stars move that fast in such tight orbits.
That was the conclusion. The observed orbits and speeds required an object that was incredibly massive, yet confined to an incredibly small space. The only known object that fits that description is a supermassive black hole. Their work provided the definitive proof.
So how massive are we talking compared to our sun?
The estimates place its mass at around 4 to 4.3 million times the mass of our sun.
4 million suns. Okay, but how big is it physically? Is it huge?
That's the mind-bending part. Despite having the mass of 4 million suns, its size defined by its event horizon, the point of no return is actually relatively small. Its diameter is estimated to be about 44 million kilometers, or roughly 14 million miles across.
That sounds big, but for 4 million suns.
It's incredibly compact. It would fit comfortably inside the orbit of Mercury in our solar system. All that mass is crushed into a region smaller than our innermost planet's orbit. Extreme density.
Is it like a cosmic monster constantly sucking things in? Is it active?
Currently, Sagittarius A is considered relatively inactive or dormant. This means it's not actively gobbling up large amounts of surrounding gas and stars right now.
So no giant glowing accretion disk like you see in movies.
Not a bright, prominent one, no. It seems to only have occasional small snacks. Maybe a gas cloud or an unlucky asteroid wanders too close, causing a brief flare of energy as it gets consumed. However, well, some recent research using X-ray telescopes like NASA's IXPE suggests it might not be completely asleep. There are hints it might have had a more significant outburst, maybe swallowing something larger just a couple hundred years ago. We might be seeing the X-ray echoes of that event now. So maybe napping is a better word than dormant.
Even dormant giants can stir. Okay, so it's got the mass of 4 million suns. Does it control the whole galaxy's rotation? Is it the gravitational king?
Surprisingly, no. What's fascinating here is that despite its immense mass, Sagittarius A accounts for only a tiny fraction, like 0.00003% of the total mass of the Milky Way, especially when you include all the dark matter.
So its gravity doesn't reach that far.
Its strong gravitational influence is really localized to the very central region, affecting only the stars and gas clouds in its immediate vicinity. The overall rotation of the vast galactic disk, the movement of stars like our sun way out in the suburbs, is governed by the combined gravity of everything. All the stars, all the gas, and especially that enormous dark matter halo. SGR-A is the anchor at the center, but it's not the puppet master of the whole galaxy.
That makes sense. And then the biz news a few years ago, we finally got a picture of it, right? Or sort of a picture.
Yes. A truly monumental achievement by the Event Horizon Telescope collaboration in 2022. They managed to capture the first ever image of Sagittarius A's shadow.
Its shadow, not the black hole itself.
Right. Black holes themselves are invisible by definition. What the image showed was the silhouette or shadow of the event horizon, cast against the bright, swirling glow of superheated gas orbiting just outside it. It was this dark central region surrounded by a lopsided ring of light, direct visual evidence confirming the theoretical predictions.
Incredible, seeing the unseeable, almost.
Exactly. And adding another layer of complexity, observations in far infrared light have revealed a strange, twisted ring of cold dust orbiting further out from the center, maybe 300 light years across, shaped like a figure 8 or an infinity symbol.
A twisted ring, what does that mean?
It's likely a remnant of past gravitational interactions, maybe gas streams being pulled in weird ways, or even debris from a past merger event. It just shows the galactic center is a really complex, dynamic, and sometimes violent place. It's amazing how much we can deduce about something so hidden.
And speaking of dynamic and violent, the Milky Way isn't always peaceful. It hosts some really bizarre high-energy phenomena, doesn't it? Things that hint at a more active past or ongoing mysteries.
Oh, absolutely. Far from serene. A great example of the Fermi bubbles.
Fermi bubbles. Okay, what are those?
In 2010, astronomers using the Fermi Gamma Ray Space Telescope discovered two enormous, previously unknown structures extending way above and way below the galactic center.
How enormous?
Each bubble stretches about 25,000 light years out from the galactic plane. So the total height of this structure is nearly 50,000 light years. They are huge, invisible lobes filled with high-energy particles glowing brightly in gamma rays and X-rays.
50,000 light years tall, just appearing out of the center. What could create something like that?
The leading theory is pretty dramatic. It suggests they are the remnants of a massive outburst from Sagittarius A itself, maybe 6 to 9 million years ago.
Our napping black hole wasn't always napping.
Apparently not. The idea is that it consumed a huge amount of material, maybe a large gas cloud or even a star cluster. And this feeding frenzy launched powerful jets of energy and particles outwards, inflating these giant bubbles, like a cosmic indigestion event on a colossal scale.
A galactic burp that left bubbles 50,000 light years tall.
Wow. Okay. What else? What about those fast radio bursts, FRBs? They sound mysterious. They are deeply mysterious. FRBs are one of the hottest topics in astrophysics right now. These are incredibly short, just milliseconds long, but intensely powerful bursts of radio waves that seem to be coming from deep space.
Where do they come from? What causes them?
That's the million-dollar question. We don't know for sure. We've detected maybe a few hundred of them now, and they seem to originate from galaxies billions of light years away. Their extreme distance and brightness mean the source must be something incredibly energetic.
Like what? Any theories?
Lots of theories. Maybe highly magnetized neutron stars called magnetars having giant flares. Colliding black holes or neutron stars. Some even speculate about extraterrestrial signals, though that's highly unlikely. The truth is, we're still gathering clues, finding more of them, like the recent batch found by Australian telescopes, HEPS, but the origin remains elusive.
Okay, so giant bubbles from our galaxy, mysterious flashes from outside.
Yeah.
What about things coming into our galaxy unexpectedly?
Yes, that's another weird one. Astronomers were searching for hypervelocity stars, stars flung out of the Milky Way at incredible speeds after interacting with Sagittarius A.
Picked up by the black hole, basically.
Right, but instead they found a surprising number of very fast stars that were actually moving towards us, barreling into the Milky Way from outside.
Incoming stars, where are they from?
They could be stars originally from satellite galaxies, like the Large Magellanic Cloud that are now passing through our galactic halo. Or maybe they were ejected from another galaxy altogether and are just cruising through. Scientists think these might be just the tip of the iceberg of a large population of these intergalactic travelers.
Cosmic visitors just zooming through. Our galaxy is less like a quiet home and more like a busy intersection.
That's a good way to think about it. The Fermi bubbles, the FRBs, the incoming stars, they all paint a picture of a galaxy that's constantly interacting with its environment, experiencing bursts of energy, and far from being a static, isolated system. It's alive in a cosmic sense.
Okay, let's zoom out again. We've talked about what's inside the Milky Way, how it moves. But what about its neighborhood? We're not alone out here, right? We're part of a group.
Exactly. The Milky Way isn't floating in isolation. It's a prominent member of a gravitationally bound collection of galaxies called the local group. Think of it as our immediate cosmic family or neighborhood.
Who else lives in the local group?
The other big player is the Andromeda Galaxy, our largest neighbor. Then there's the Triangulum Galaxy, the third largest spiral. And surrounding these three larger galaxies are dozens, probably over 50, maybe even more smaller dwarf galaxies.
Like the Magellanic Clouds.
Yes, the Large and Small Magellanic Clouds are two of the most famous satellite galaxies orbiting the Milky Way, part of this local group structure. The whole group spans about 10 million light years across.
10 million light years. Still huge, but small compared to the universe. Is the local group itself part of something even bigger, like a galactic city or state?
It is. The local group is just one small cluster within a much larger structure called the Virgo supercluster. This contains thousands of galaxies and spans over 100 million light years.
Okay, so we're in the local group, which is in the Virgo supercluster. Does it keep going?
It does. In 2014, astronomers realized that the Virgo supercluster itself is just one lobe of an even more immense structure, a supercluster they named Laniakea, which means immense heaven in Hawaiian. Laniakea contains about 100,000 galaxies and stretches over 500 million light years.
Laniakea. 500 million light years. That's our cosmic continent, basically.
Essentially, yes. The universe on these largest scales looks like a giant cosmic web, filaments of galaxies and clusters connecting dense nodes, separated by vast, mostly empty regions called voids.
And where are we in this web? Are we in a busy filament or an empty void?
Surprisingly, we seem to be in a void, or at least on the edge of one. Our local group appears to reside within a large, relatively underdense region known as the KBC void, Keenan, Barger, and Cowie void.
We live in a cosmic empty spot. That's unexpected.
It is a bit counterintuitive, yeah. We're not in one of the major cosmic superhighways.
Okay, back to the local group and our satellite galaxies. You said the Milky Way has over 50. Do they just orbit peacefully?
Not always peacefully, no. This brings us to a rather dramatic process called galactic cannibalism.
Cannibalism. Our galaxy eats other galaxies.
It does, and it has been doing so throughout its history. That's actually a major way that large galaxies like the Milky Way grow, by gravitationally capturing and absorbing smaller dwarf galaxies that stray too close.
So we're galactic predators. How do we know this happened?
We see the evidence. Using data from Gaia, astronomers have found streams of stars within our galaxy that move differently from the bulk of Milky Way stars. They have different orbits, different chemical compositions. These are the shredded remnants of dwarf galaxies that were torn apart and absorbed billions of years ago.
Like the Gaia sausage you mentioned earlier.
Exactly. That's a prime example of the leftover stars from a dwarf galaxy eaten long ago. And we see it happening now. The Sagittarius dwarf galaxy, for instance, is currently being ripped apart by the Milky Way's gravity. We can see long tidal streams of its stars being pulled off it as it orbits through our halo.
Wow, so we're literally watching our galaxy have a meal right now in slow motion over millions of years.
That's exactly what's happening. The Canis Major dwarf galaxy is another one currently being assimilated. These stellar streams are like glowing breadcrumbs tracing the path of destruction.
And that dwarf galaxy, Leo first, with the unexpectedly huge black hole, could that be a future meal?
It's possible. Scientists are studying if its orbit will eventually bring it close enough to be disrupted and merge with the Milky Way.
Yeah.
If that happens, its supermassive black hole could eventually merge with Sagittarius A, which would be quite an event.
Is our Milky Way typical in this cannibalistic behavior? Or maybe in how many satellites it hasn't eaten yet?
That's an interesting point. The Saga survey, looking at galaxies similar to ours, found that the Milky Way might actually have an unusually low number of bright satellite galaxies compared to its peers.
Really? Why would that be?
One idea is that the Large Magellanic Cloud, our biggest satellite, only fell into our orbit relatively recently, maybe 1.5 billion years ago. Perhaps we just haven't had time to capture as many large satellites as other similar galaxies. It raises questions about whether our local group is truly representative or maybe a bit of a cosmic outlier.
It just shows galaxies aren't static islands. They're constantly interacting, merging, growing, changing. It's a dynamic cosmic ecosystem.
Perfectly put.
And speaking of dynamic interactions, the biggest one on our horizon is the collision with Andromeda, right? Our biggest neighbor is heading straight for us.
That's the big one, yes. The Andromeda Galaxy, which is, as we discussed, a bit larger than the Milky Way, is currently moving towards us at a very high speed, around 110 to 140 kilometers per second.
250,000 miles an hour or more? Yikes. Collision is inevitable.
Based on measurements from the Hubble Space Telescope tracking Andromeda's sideways motion, or lack thereof, yes, a future collision seems inevitable.
When? Do I need to update my insurance?
Aha! No, you've got plenty of time. The collision is predicted to begin in approximately 4 to 4.5 billion years from now.
4 billion years. Okay, panic over. What will it actually be like? Is it going to be stars crashing, explosions?
Not really like that. It's a common image, but incorrect. Because the distances between stars within galaxies are so incredibly vast, direct star-on-star collisions will be extremely rare. Maybe a handful at most.
So it's not a crash, but a merger.
Exactly. It will be a slow, gravitationally driven cosmic dance lasting billions of years. The two spiral galaxies will pass through each other, their structures getting stretched and distorted by gravity, forming long tidal tails. They'll swing back around, pass through again, maybe several times, gradually losing energy and merging together.
And the end result? What do we become?
The two spiral galaxies will eventually merge into a single, much larger, potentially more disordered galaxy, likely an elliptical or lenticular galaxy. Some astronomers have playfully nicknamed this future galaxy Milkomeda.
Milkomeda, I like it. What happens to us, to our solar system during this? Do we get destroyed? Flung out?
NASA simulations suggest that while the Sun will likely be thrown into a completely different orbit within the new Milkomeda galaxy, perhaps much further from the core, the solar system itself, the Sun and its planets, should remain intact. The chances of another star passing close enough to disrupt the planets are very low.
So we'll survive just with a very different night sky and a new galactic address.
Pretty much.
And the supermassive black holes. Sagittarius A and Andromeda's central black hole.
They will eventually find each other too. After the main galactic merger, the two black holes will spiral towards each other over millions of years, emitting powerful gravitational waves before finally merging into a single, even more massive black hole at the heart of Milkomeda.
A merger of giants. And you mentioned recent studies suggest Andromeda might not be much heavier than the Milky Way after all. Does that change things?
It makes the merger seem more like a collision of equals rather than David versus Goliath. It might affect the exact final structure of Milkomeda, making it perhaps less dominated by Andromeda's original structure. And studies of other merging galaxies suggest the process might be even more complex than simple simulations show, possibly involving interactions with all the smaller satellite galaxies getting tossed around during the merger too. It could be a chaotic multi-body dance.
So this grand cosmic ballet happening on timescales we can barely comprehend. It's just another reminder of how dynamic and ever-changing the universe is. We're living through one small chapter of an epic story.
Beautifully said.
Which brings us, inevitably, to the biggest question of all, doesn't it? With billions upon billions of stars, likely trillions of planets, is there life out there? Are we alone in this vast Milky Way?
That's the ultimate question, the one that drives so much exploration and wonder. And based on what we're learning, the potential seems enormous.
We know planets are common now, right? It's not just speculation anymore.
Absolutely. Thanks to missions like Kepler and TESS, we now know that planets are incredibly common. Most stars likely have planetary systems. We've confirmed thousands of planets outside our solar system just in our little neighborhood of the Milky Way.
And many of those are in the habitable zone, the Goldilocks zone.
A significant number, yes. The habitable zone is that region around a star where temperatures could potentially allow liquid water to exist on a planet's surface. Not too hot, not too cold, just right. And finding rocky planets in that zone is a major focus.
And there's even a galactic habitable zone idea, like a Goldilocks zone for the whole galaxy.
Kind of, yeah. It's a more complex concept, considering factors beyond just temperature. It suggests there might be a ring-shaped region within the Milky Way that's most conducive to life.
Why a ring?
Well, you need enough heavy elements, metals, to form rocky planets, which are more abundant closer to the galactic center, where more star formation has happened. But you also want to avoid regions with too much deadly radiation, like frequent supernovae, or the intense radiation near the galactic core. So there might be a sweet spot not too close to the center, not too far out in the metal-poor fringes, where conditions have been stable and suitable for complex life to arise and persist for billions of years.
Okay, so planets are common, habitable zones exist, maybe even galactic sweet spots, which leads directly to the Fermi paradox. If the potential is so high, where is everybody?
That's the heart of it. Named after physicist Enrico Fermi, who famously asked something like, "If life is common, why haven't we seen any sign of it?" Given the age of the galaxy and the sheer number of stars, you'd think some civilization would have risen, become advanced, and left some detectable trace, whether intentional signals or unintentional artifacts. But silence. Cosmic silence.
Is anyone actively listening or looking?
Yes, that's the goal of SETI, the search for extraterrestrial intelligence. Various projects scan the skies, mostly using radio telescopes, hoping to pick up artificial signals that couldn't be produced by natural astrophysical phenomena. So far, nothing definitive.
And the Drake equation tries to estimate the odds, right?
Right. The Drake equation is a framework, really. It multiplies together several probabilities: the rate of star formation, the fraction of stars with planets, the fraction of planets that could support life, the fraction that do develop life, the fraction that develop intelligence, the fraction that become communicative, and the average lifespan of such a civilization.
Lots of unknowns in there.
Huge unknowns. You can plug in optimistic numbers and get estimates of thousands, even millions of civilizations in the Milky Way right now. You plug in pessimistic numbers and you might get, well, one. Us. Some recent estimates, trying to be realistic, suggest maybe a few dozen technological civilizations currently active, but likely very far apart, maybe hundreds or thousands of light years.
So maybe they exist, but they're just too far away, or we're not looking at the right time, or using the right methods.
Those are all possibilities. Or maybe civilizations don't last very long once they become technological. Or perhaps life itself is common, but intelligent, technologically advanced life is exceedingly rare.
Which leads to the rare Earth hypothesis.
Exactly. This hypothesis argues that while simple microbial life might be common, the specific combination of circumstances needed for a complex, multicellular, intelligent life like ours to evolve might be incredibly rare. It requires not just a planet in the habitable zone, but maybe a large moon for stability, plate tectonics, the right planetary neighbors like Jupiter acting as a cosmic vacuum cleaner, the right position in the galaxy, a whole long list of potentially low probability events all happening in the right sequence.
So maybe we are incredibly lucky, or incredibly unusual.
It's possible. The ongoing discovery of diverse exoplanets keeps fueling the debate. Every new discovery refines our understanding, but the ultimate answer to, are we alone, remains one of the biggest, most profound questions we can ask.
What a journey we've taken today. Seriously. We've gone from ancient myths about spilled milk to supermassive black holes and galactic cannibalism. We've explored the Milky Way's name, its mind-boggling size and warp shape.
Talked about the stars, the gas, the dust, that mysterious dark matter holding it all together.
tracked our own solar system's incredible high-speed journey around the core, looked at the Fermi bubbles and FRBs.
And even peeked into our cosmic neighborhood and the galaxy's dramatic future collision with Andromeda.
It really shows our galaxy is anything but a static backdrop. It's this ancient, massive, constantly evolving system, a masterpiece of cosmic creation, destruction, and rebirth.
And the most incredible part, perhaps, is that we're here, inside it, on this one small planet, trying to piece together the story of this immense home we inhabit.
Yeah, the Milky Way's beauty, its complexity, its mysteries, they just keep pulling us in, don't they? Reminding us how much more there is to learn about the universe.
Absolutely.
So here's a thought for you listening. What new, maybe even unimaginable discoveries about our own galaxy do you think we'll make in your lifetime? Will we finally figure out dark matter? Find evidence of life beyond Earth? See something completely unexpected?
It's an exciting time for astronomy. The next generation of telescopes, both on the ground and in space, promise to reveal the universe in ways we've never seen before. Who knows what secrets the Milky Way still holds?
Keep looking up, keep asking questions, and keep exploring. We'll see you on the next deep dive.